Welcome. This is part 2 of the extended Maxwell Boltzmann distribution series. In part 1, we explored the distribution in integer dimensions. In part 2, we'll see that the same formulas can also be applied to non-integer dimensions. When d equals 1, the extended Maxwell Boltzmann distribution becomes the normal distribution. When d equals 2, it becomes the Rayleigh distribution. At d equals 3, it turns into the standard Maxwell-Boltzmann distribution. This can be extended to any integer greater than 3. The extended Maxwell-Boltzmann distribution isn't limited to just integers. It can also be applied to non-integer values. For example, d can be 1.5, 2.5, 3.5, 4.5, 4.6, 4.7, and so on, even up to very large numbers. The extended Maxwell-Boltzmann distribution formula can be used for both integer and non-integer values of d. The key idea behind this extension is that it allows the dimensionality, d, to go beyond just integers and take on non-integer values as well. Here are 3 examples of the Maxwell-Boltzmann distribution for integer values. The figure on the left shows the distribution for dimension d equals 3, with root mean square speeds VRMS equals 2 and 4. The middle figure shows the distribution for d equals 4, and the figure on the right shows it for d equals 5. When d equals 3.5, the gamma function becomes tau, 3.5 divided by 2, which equals 3.323. The figure shows the distributions for d equals 3.5 with VRMS equals 2 and VRMS equals 4. When d equals 4.5, the gamma function becomes tau, 4.5 divided by 2, which equals 11.631. The figure shows the distributions of d equals 4.5 of VRMS equals 2 and VRMS equals 4. Similarly, when d equals 5.5, the gamma function becomes tau, 5.5 divided by 2, which equals 52.342. The figures show the distributions of d equals 5.5 of VRMS equals 2 and VRMS equals 4. Here, we combine the extended Maxwell-Boltzmann distributions to see if the transition between integer and non-integer values of d is smooth. The top row shows integer values of d, 3, 4, and 5, while the bottom row shows non-integer values, 3.5, 4.5, and 5.55.5. As you can see, the transition between integer and non-integer d is very smooth. The equipartition theory states that a monatomic gas has 3 degrees of freedom, while a diatomic molecule has 5. So why do we need a non-integer dimension, d? Equipartition alone can't explain why some experimentally observed values of d are non-integer. Measurements show that diatomic molecules often have a dimension d between 3 and 5, and polyatomic particles have d values greater than 5. We can define the total dimension d as 3 alpha, where alpha is defined as the ratio of the total kinetic energy to the translational kinetic energy. Also, the total kinetic energy is the sum of the translational kinetic energy, ET, and rotational kinetic energy, ER. Based on this definition, for a diatomic particle, alpha, the ratio of total kinetic energy to rotational kinetic energy is 5/3, which results in a total dimension d of 5, which agrees with the equipartition theorem. Similarly, for a monatomic particle, the ratio of total kinetic energy to rotational kinetic energy is 1, which results in a total dimension d of 3, which also agrees with the equipartition theorem. In summary, the total dimension d in the extended Maxwell Boltzmann equation can be either an integer or a non-integer value. This total dimension can be formulated as 3 alpha, where alpha is defined as the ratio of the total kinetic energy, ET plus ER, to the rotational kinetic energy, ER. This concludes part 2 of the extended Maxwell Boltzmann distribution. Thank you.